Hey everyone, let's prove Theorem 4 from Lecture 4, aka Theorem 1.2 from Section 1.2. It says, consider integers a and b not both 0 and their greatest common divisor d. And there exist integers u and v such that d is a linear combination of a and b. d equals au plus bv. Now the proof, which is in the book, involves two steps. First, we show that the set of all linear combinations of a and b, we're going to call it S, has the smallest positive element. And then second, we show that that smallest positive element is the greatest common divisor. Okay? So first, we show S is non-empty. Well, the way we do that is note that if you let u equal a and v equal b, we have au plus bv equals a squared plus b squared, which is strictly greater than 0 because a and b aren't both 0, right? So we have that it's strictly positive. So a squared plus b squared is in S. And then by the well-ordering axiom, which you can find in Appendix C if you'd prefer, if you'd like. Remember, that's where we learned induction. We see S has a smallest element. And we're going to call that element T, okay? So for some u and v in the integers, right? For some integers u and v, we have t equals au plus bv. And remember, t is the smallest such element, like this, okay? So now we're going to show that t is the GCD of a and b. So now, first, we're going to show that t divides a and t divides b. And the way we're going to do that is by showing that t divides a. It's going to be a little bit drawn out, but then we'll just say symmetrically t divides b. It's the same thing. So we'll say by the division algorithm, for integers q, or I guess I should say for integers q and r, we have that a equals qt plus r for and the one restriction we do have is that r has to be between 0 and t, right? It could be 0, but it can't be t, right? It's got to be strictly less than t, right? Okay, so I guess we could say that since t equals au plus bv, we also have that this is equal to q times au plus bv plus r. And I guess we did a bit of subtraction, right? Subtracting stuff over, you can see that this is the same as saying r equals a minus qt, or qa u plus bv, right? And then you can sort of regroup and distribute the negative sign, distribute the q, factor out the a, and you wind up getting 1 minus qu minus b, or I should say, sorry, plus b times negative qv. You can pause the video if you don't see that, but just do it out, right? And this is important because we have a times something plus b times something. R is a linear combination of a and b, right? We can write this as a big U plus b big V for u and v in the integers, right? So that would mean that r would be in T. Except not really, because that would mean that r would be in S. Except that's not possible because r is less than T. We cannot have r in S. Well, then the only way that that could be the case is if r isn't positive, which means that r has to equal 0. Okay? Well, what does that mean? That means that T divides A. And I'll just say analogously or symmetrically, we can see that T divides B. Okay? So we've shown that T is a divisor of A and a divisor of B. We just want to show that it's the greatest. Right? Show that it's the greatest common divisor of A and B. To show that, suppose that C divides A and C divides B. Now we want to show that C is less than or equal to T. All right, that's the other part of the GCD. Now you might recall that further on, we actually proved something a little bit stronger, right? We need to just show that C divides T. But because we didn't prove corollary 1.3 yet, that's a corollary of this theorem, let's just prove the old-fashioned way that C is less than or equal to T, okay? So that means that T equals AU plus BV, right? Again, that's the definition of T, right? The smallest such one, right? And I guess we know that that equals CKU plus CLV, right? For some integers K and L, right? Because C divides A and C divides B, right? Again, we're using the definition of a divisor, right? And that implies that T equals C times the quantity KU plus LV. So what that means then is that C divides T. And so C is less than or equal to the absolute value of T, except that we define T as being positive, right? It's the smallest elements of S, just positive numbers. So actually C is less than or equal to T. So T is the greatest common divisor of A and B. Whoop, that's a D, not an L. There you have it.